in this video, I've used the phrase take the leap, and in this video I actually want to take the leap and show you why these things are so useful to us. So a function like sine of 2x over x, if I wanted to find the area under that from 0 to 1, notice this is not something we know how to integrate. Okay, substitution won't work. You can't rewrite it and use partial fraction, or integration by parts. This is something we can't work with. So I am going to replace the sine of 2x over x with a series. Okay, so I'm going to make a note here. We're going to replace this. So you notice that this thing starts at 0, so I'm going to replace with a Macluarin series, because I think that will be easy and it'll be exactly correct at 0. And I'm just going to use like 3 terms. I'm not going to go too in depth with this. But let's start with the sine of x. Okay, the sine of x, remember, is approximated with this series. And again, I'm putting the approximation thing instead of equal because I'm only going to do 3 terms. Okay, so the sine of 2x, well, everywhere we saw an x, we'll just write 2x. Now 2x cubed, so 8x cubed over 3 factorial plus 32x to the 5th over 5 factorial, like that. Now this said that we take the sine of 2x, and again, this is our approximation for that. It says we take that and we divide it by x. Well, I'm going to do that. I'm just going to divide both sides by x. Okay, well, 2x divided by x is 2. 8x cubed over 3 factorial, well, this is going to be 8x squared over 3 factorial, because you divided an x out. And then we're going to have 32x to the 4th over 5 factorial. And maybe now we want to do some reducing. Okay, so we have 2 minus 8 over 6 is 4/3 x squared. And 32 over 120 reduces to 4/15, like that. So here is our just quick, easy approximation of that original function. Okay, so I can't integrate that original function, but I can integrate this approximation. So here's what I'm going to do. I'm going to say that this original integral is approximately the same as the area from 0 to 1 of this approximation. Okay, so let's find the antiderivative. 2x minus 4/9 x cubed plus 4 over 75 x to the 5th. And we're evaluating at 1 and 0. So if I plug in 1, I get 2 minus 4/9 plus 4/75. If I plug in 0, I get 0. And if I do that, if I get the common denominator and work through it, I get 362 over 225. Which, if then you go back and you use fn_int to do this, if you want to compare them, they are 3/1000ths away from each other. And I'm going to drag this in to just show how close they are from 0 to 1. You can see my original graph is in red. You can see that the approximation that I made is, and I didn't even reduce it here, is in blue. And you can see from 0 to 1, they are slightly different at the end, but of course it was Maclaurin, so they're perfect at 0. If I'd added one more term, I would have gotten even better. Okay, so this is just, really, this is the purpose in doing a Taylor series, or a Maclaurin series in this case, is to be able to take a function that we couldn't work with, we couldn't find the area under it, and essentially just replace it with a function we can work with.